Good morning students. Welcome to YouTube channel Next is You. In the last class we discussed about Poisson's equation. Poisson equation tells us the electric potential at any point depends on the amount of charge present in that region. Now physical interpretation of Poisson equation is imagine placing a positive charge in a space. The charge creates an electric field around it. The electric field creates a potential distribution. Now this Poisson's equation mathematically describes this relation. Now we have a Poisson's equation del square V is equal to minus rho upon epsilon naught. Suppose the charge density is constant, so rho is equal to rho naught. Here we use rho naught in place of rho. So d square V upon dx square is equal to minus rho naught upon epsilon naught. Now this d square V upon dx square is for one dimension. Now integrating this equation with respect to x, we have dv by dx is equal to minus rho naught x upon epsilon naught plus c1. Again integrating this, we have v is equal to minus rho naught x square upon 2 epsilon naught plus c1x plus c2, where c1 c2 are the constant, and where we have a quadratic equation, we have a term of x in squares. So the potential is now parabolic and showing that the presence of charge changes the curvature of the potential. In this video we will discuss about the Laplace equation and also find out the potential corresponding to Laplace equation. So we start with derivation of Laplace equation. Now del square V is equal to minus rho upon epsilon naught is the Poisson equation when there is no charge. Rho is equal to 0, so we have a Poisson equation del square V is equal to 0 upon epsilon naught, which is del square upon V is equal to 0. This del square V is equal to 0 is the Laplace equation. Now the physical meaning of Laplace equation: in the region without charge, where there is no charge, no new electric field is produced. The potential is determined only by the surrounding boundaries because there is no charge inside the boundaries, and we can determine potential only by the surrounding boundaries. For example, the space between two charged conducting plates contain no free charge, so the potential there satisfies Laplace equation. Difference between Laplace and Poisson equation. Here we have a Laplace equation, here is the Poisson's equation. It validates when there is no charge. This equation validates when charge is present. This equation is homogeneous in nature, this is non-homogeneous equation. Here the solution of the equation is simple, more general equation. This depend on a boundary condition, and Poisson equation depend upon charge distribution and boundary conditions. Now understanding the Laplace operator del square. So the del square measures how much the value of function at a point differs from the average value around that point. Suppose this is a point and there is a value of a function. Now there are many other points around this point, so the average value of all the points from a function is differ with this point value. This difference measures by a Laplace operator, and in electrostatics it tells us how the electric potential curves in space. Cartesian coordinates for del square V is equal to curl square V upon curl x square plus curl square V upon curl y square plus curl square V upon curl z square. Each second derivative shows how the potential changes along one direction. Now the solution for this Laplace equation, we have Laplace equation for x-axis d square v upon dx square is equal to 0. Now integrating this equation, we have dv by dx is equal to c1. Now integrating again this equation, we have v is equal to c1x plus c2, where c1 and c2 are the constants. Now this equation is compared with the line equation, which is y is equal to mx plus c. So the potential changes linearly with the distance. So it has a comparison, this equation has a comparison with the line equation, straight line equation. Now if we take an example where we have two plates, one at a lower potential that is 0 volt, other is at 100 volt that is a higher potential. The separation between the two plate is d. Now we already studied in the previous lecture that potential at a distance x from a lower plate, we have Vx is equal to V naught dx, and x lies between 0 and d. Now if we plot a graph between V and potential and separation d, we get a linear straight line. So the potential varies linearly from 0 to V naught, and we use these values in this formula. We get Vx is equal to 100x upon d. The graph of potential versus distance is a straight line. The electric field, we can calculate electric field by getting a derivative of this potential with respect to x. We have E is equal to minus dV upon dx, which is equal to minus 100 upon d. Now this 100 upon d is a constant, so the derivative is constant, the electric field is uniform. If we take an example that a region is free of charge, so if the region is free of charge, we have a equation, Laplace equation, and potential varies only along the x-axis. If potential varies only along the x-axis, find the potential if we have a boundary condition. V is equal to 0 at x is equal to 0, V is equal to 100 volt at x is equal to 10 centimeter. Now when there is no charge inside the region, we have d square V upon dx square is equal to 0. General solution for Laplace equation is V is equal to C1x plus C2. Now first boundary condition is V is equal to 0 at x is equal to 0. So we have V is equal to 0 and x is equal to 0. So C2 is equal to 0. Now second condition, x is equal to 10 centimeter, potential is equal to 100. So 100 is equal to 10 C1, and here we have C1 is equal to 10. Now putting these values C2 and C1 in equation V is equal to C1x plus C2, we get V is equal to 10x. Now the electric field, now take a derivative of this potential, we have E is equal to minus dV by dx, which is equal to minus 10 volt upon centimeter. Now this negative sign indicates that electric field points toward decreasing potential. Now there are some tips we have to remember. This goes law to derive a Poisson's equation, and Poisson plus no charge is equal to Laplace. Solution of Laplace equation are called harmonic function. Laplace equation is homogeneous, Poisson's equation is non-homogeneous. In one dimension, Laplace equation gives a linear potential, Poisson equation gives a quadratic potential. Boundary conditions are very essential for obtaining a unique solution for both Laplace equation as well as the Poisson equation. Now memory trick, Poisson presence of charge. So P for Poisson, P for presence of charge. Laplace lack of charge, think of letter L, L for Laplace, L for lack of charge. Charge density not equal to 0 in case of Poisson equation, charge density equal to 0 in case of Laplace equation. Now the electric field, there are some formulas which we can use for in next class to solve solutions. That is E is equal to minus del V, Poisson equation del square V is equal to minus rho upon epsilon naught, Laplace equation del square V is equal to 0. We will calculate the potential for Poisson equation and Laplace equation by using a boundary conditions. For Poisson's charged region, for Laplace has a charge free region. For one dimension Laplace solution, straight line potential, one dimension Poisson solution, parabolic potential. So this is all about the Laplace and the Poisson's equation. In the next class we will discuss about the boundary value problems, and with the help of these boundaries we will find out the potential corresponding to Laplace as well as Poisson's equation. Thank you and have a nice day.